Great, so welcome everyone to this talk. So let me give you a quick upfront idea about what this talk is going to be. So I'm essentially going to describe a set of modifications we made to Spark to enable Spark to run arbitrary workloads like machine learning workloads, obviously, like the title says, but also SQL workloads, MapReduce workloads in a serverless fashion, right? That's just to put the talk into perspective because I've been told the title is a bit misleading. So I also want to point out that a lot of the work I'm presenting today has contributions from a larger team at IBM Research. In particular, I want to mention Michael Kaufman and Adrian Schippach. They have put a lot of work into this to make this happen. So let me start with this. So I assume most of you guys are familiar with the term serverless computing, which is a new execution model, if you want, that dramatically simplifies both the development as well as the execution of parallel applications in the cloud, right? So the basic idea of serverless computing is that it frees developers from having to set up or manage clusters of machines. Instead, the serverless framework will automatically launch the necessary infrastructure for you, find out the right amount of resources to provision, possibly adjusting the resource pool by scaling it up and down dynamically based on the load, etc. And there are plenty of serverless frameworks out there like AWS Lambda, Google Cloud Functions. Pretty much every big cloud operator has a serverless programming interface, right? And using these interfaces is not only making life simpler for the developer, but it's also typically cheaper because as a user, I'm only going to be charged for the resources I'm actually using instead of being charged for a set of machines that may be idle at any point in time. So serverless computing has all these nice properties. One big challenge with serverless computing, though, is performance. If you take a particular workload, running that workload on a serverless framework typically takes longer than running the same workload on a dedicated cluster. And this is illustrated by this figure using a simple MapReduce type of application that sorts 100 gigabytes of data. It's kind of a classic application that is used a lot to show certain things. We start with this application and then later on move to more complex workloads like machine learning and so on. But so far, what this figure shows, the bar on the very left-hand side, is showing an implementation of the sorting application for the AWS Lambda serverless framework. So it's a general purpose serverless framework. And you can see it takes about 500 seconds to sort 100 gigabytes of data, right? So about 8 minutes. What the application does, essentially, it is reading the input data from an S3 object store, sorting it in parallel using about 64 parallel workers at the map stage, and then writing it out in a sorted manner on S3 again in the end, right? And now the second bar on this figure, so we're going to walk from the left to the right. The second bar of this figure shows another implementation of such a sorting application, this time implemented for Spark and deployed using the Spark serverless offering, right? So Spark Serverless allows you to configure serverless pools of machines. These pools can grow and shrink dynamically. You can multiplex them. You can share these pools by multiple applications. In this case, we configured a serverless pool with 1 to 8 machines, each machine having about 8 cores. So this is roughly matching the configuration we've used for the AWS Lambda experiment, where we have been using 64 workers, each running on a single core, right? And what you can see is that on the serverless, Databricks serverless offering, the same type of workload takes less time, obviously, and this is making sense, right? Spark obviously is optimized to run that type of workload. Now, if we move to the third bar in the figure, this is the very same application, but this time we executed also on the Databricks cloud, but we use a standard cluster, a fixed size cluster of 8 machines. And you can see we can bring down the performance quite a bit. And this is partially because in this configuration, resources are no longer added on demand. This is what happened in the serverless case. Some of the executors, they actually got added after a few minutes into the job. Right? Using the standard cluster, the executors are provisioned from the very first moment the application starts, and they're engaged in processing that job. So that helps to improve the runtime. The bar next to that, the second bar from the right, is showing another implementation of the sorting application. But this time we deploy it on-premise on a self-managed cluster that is equipped with top-of-the-line hardware. So what is top-of-the-line hardware here? It's pretty fast network, so we're running a 100 gigabit network, plenty of flash, plenty of DRAM. This is a pretty good cluster, right? So we can bring down the runtime further quite a bit with this. And then the last bar in this figure is showing the same cluster, but this time we are throwing in some optimizations at the software stack. So we are running an optimized network stack, an optimized storage stack. Essentially, we're using RDMA and all these kind of nice goodies here for this last configuration. If you're interested in getting more information about that particular setup, there's a Spark Summit talk from last year that has all the information about how this setup is, how that configuration is set up. But the basic takeaway from that figure is, as we move from a flexible, easy-to-use setup, like the AWS Lambda setup or the Databricks serverless setup, to a statically configured on-premise cluster, we lose flexibility on the one hand side, but in return, we gain performance, a substantial amount of performance. It's about a 30x factor between the serverless setting on the very left and the on-premise optimized cluster on the right-hand side. So clearly, what we would want is the flexibility of the serverless framework, but combined with the performance of a dedicated cluster running on pretty fast hardware. So this is kind of what this talk is about. But while talking, I forgot to navigate through the slides. Sorry about that. So now let's have a look at why performance is so hard to achieve, right? What are the performance limiting factors? And there are multiple aspects in a serverless framework that have performance implications. For instance, when should we add and remove resources, right? That's a question a serverless scheduler has to answer, and if you're making suboptimal decisions there, you may lock up resources in one application that could otherwise be used more effectively in a different application. Then container startup time is a known issue. I mean, many serverless frameworks use containers for isolation. They execute functions inside containers. Starting a cold container can easily add an overhead of several hundreds of milliseconds. And then storage is another performance limiting factor. Serverless frameworks typically require tasks to read input data from a remote storage source. Remember, in the sorting application, we read the input data set from S3 in the first place. And that's fundamentally different from a cluster setup using HDFS, for instance, where the storage nodes are co-located with the compute nodes, and task scheduling is based on data locality, right? Also, in the serverless case, typically the intermediate data, that is like shuffle data in Spark or broadcast data, that data needs to be stored on a remote storage service as well, and these are extra storage operations that cause extra overhead in a serverless setting. And this is illustrated here also by this figure, using the sorting app again. First, for the cluster setup, you can see all the storage operations are shown in red. So in a cluster setup, pretty much all storage operations except in the reduce phase, where data is fetched from the mappers, all I/O operations, if you want, are local, right? Obviously, this is an ideal setting. In practice, you may not be able to schedule all tasks completely local, right? Anyway, in a serverless setting, the picture looks pretty much like this. You have input data, intermediate data, as well as output data that needs to go and come from an external storage source, right? And that is expensive. So at this point, you may wonder, where does this requirement for remote storage come from anyway, right? And the answer is, it's less of a requirement than an optimization. If you keep all data and state on a remote storage location, it's much easier to scale the compute cluster up and down dynamically as the job goes on. That's kind of the answer to this. Now, obviously, doing all these storage operations is not free, right? How much does it cost in terms of performance? This is showing how time is spent for some of these experiments we have just discussed. So you can see on the very left side, for the Amazon Lambda experiment, about 60% of the time is spent on shuffle-related operations. And this is not including the actual sorting that is happening in a shuffle operation. This is just really only the storage operations. And on the other hand, you can see in a cluster setup, only about 30 to 40% is spent on shuffle-related I/O operations. And that is in a run that already has a much lower runtime in absolute terms. Now, so far we have discussed sorting, MapReduce, right? What about other workloads? This is a snapshot of a SQL query, one of the queries from the TPCDS benchmark. And obviously, it looks way more complicated than a simple MapReduce job, and it also has quite a bit more shuffle and broadcast operations. In fact, this snapshot is not even showing the entire query. It's just a subset. I couldn't pack the full query on the screen really for this talk. And this is showing a machine learning workload, right? A distributed machine learning workload. Most distributed machine learning workloads follow such an iterative pattern. I'm sure you guys are familiar with this. So time is divided up into epochs. In each epoch, the training data is read from an input source. The new gradients are computed. The model is being updated, and the new model is being fetched, right? And typically you have the model being stored at a parameter server or at a set of parameter servers. And if you're running such a setup, you may want to apply certain optimizations. For instance, you may want to shard the model over multiple parameter servers. One common optimization is to co-locate the parameter servers with the worker nodes so that at least some worker nodes can avoid updating the model over the network. And also for the input training data, right? For the input training data, right? You want to cache that in the host memory of the workers, so you don't want to read the training data in every epoch again, right? Now, if you think about a serverless setup, right? Some of these optimizations cannot easily be applied. So for instance, it's no longer possible to co-locate the parameter servers with the worker nodes, right? Why not? Because the worker nodes, they are part of a compute cloud that dynamically grows and shrinks. So we cannot have the parameter servers part of that set. Also, we cannot assume the training data set to be cached, right? One task may execute on one particular machine in one epoch, and the same task operating on the same data partition may execute on a different machine in the next epoch, right? And if this is happening, then the training data has to be read again from the input source. And because machine learning workloads, or most machine learning workloads, if they're running in a synchronous manner, an epoch is basically a synchronization barrier. So any overhead of one task will basically stall the entire epoch, right? So by now, I hope you have a good understanding of why it is difficult to operate a serverless deployment in an efficient manner. In particular, if you want to support arbitrary workloads, right? As part of the work I'm presenting here today, we have been exploring whether we can turn Spark into a serverless framework, right? Can we use Spark to run machine learning, SQL workloads, etc., in a serverless fashion? And also make sure that we get the performance out that is basically identical with the performance you would see if you run these workloads on a dedicated cluster. Right? This is kind of the goal we had for this work. We figured out that turning Spark into a serverless framework requires us to make fundamentally change two pieces, namely the scheduler in Spark, the task scheduler, and the way intermediate data is handled, right? So And for both of these pieces, there are multiple design options we looked at. For the scheduling, for instance, one option would be to basically build a Spark serverless framework as a wrapper on top of an existing cloud-based serverless framework, like AWS Lambda or so, and then use that framework to launch Spark executors, right? But that's not what we want, because then each job will basically have to wait until these executors are booted, and what you expect from a serverless framework is that you can actually run your jobs instantly without having to wait for infrastructure to boot, right? So we basically dismissed that option. The second option is we could have built a new type of executor, right, which takes the tasks, and instead of running the tasks on the local CPU, the tasks are run on a cloud serverless framework, right? That, again, is, I think, a bad idea, because we would end up running Spark tasks in a container, right? This is like this would be terribly slow in the end. So we decided eventually to add serverless functionality to the Spark runtime by enabling Spark to share, to enable Spark to share different executors with different applications. So this is kind of like a little bit abstract right now. It will become more clear in a few more slides. But basically, we changed the parts of Spark so that a driver can be associated with a different set of executors at any point in time, and that assignment can be changed. The second design, the second piece, the component we had to kind of think how to change it was how should we handle intermediate data. And one option would be to basically allow Spark executors to cooperate with the scheduler. So have the scheduler inform the executors about upcoming scale out to scale in events, right? So that the schedulers, if they get informed about this, they can push out all their local state to a remote storage location. That would be one option. We consider that to be rather complex to implement. Instead, what we choose is a much simpler approach, that is to consequently store all state and intermediate data at remote locations, but make sure that these storage operations are implemented very efficiently at very low latency, so that we can almost ignore the overhead of these operations. And this is showing a picture of the complete system, right? It's basically three modifications, if you want, to Spark. On the one hand side, we replaced the task scheduler in Spark with our own scheduler. This is the HCS scheduler here in this picture, right? HCS stands for heterogeneous cluster scheduler, right? And the name reflects the fact that the scheduler is capable of taking heterogeneous hardware into account. Like, it can differentiate between nodes that have a CPU and nodes that have a GPU, right? And this is important for machine learning workloads. The second modification we made to Spark is we changed the Spark driver so that the driver can be associated with different set of executors, and that association can be changed as the job runs. I will make an example about that in a second. And the third modification we made is as I said, we made sure that all intermediate data, like shuffle data, broadcast data, etc., is stored on an external data store. We chose to run this on Apache Grail. This is a new incubator project in the Apache domain. Grail is essentially a data store that is designed for high-performance hardware, like RDMA, NVMe flash, and so on. It is beyond the scope of this talk to give a detailed introduction into Grail. I have a link in the end to the Grail website that has more information, right? So Grail effectively runs on high-performance hardware, but Grail can also run in the cloud using on standard hardware. It's just going to be a bit slower. So to give you an idea how an application is executed on this deployment, remember that in Spark, an application is basically represented by a driver, right? Or the code that runs in the driver. So here we have three applications represented by these different colors, right? And you can see that at this point, the orange application is associated with 2 executors, right? And what we essentially do is we keep changing that association over time. First of all these applications are basically multiplexed on the same set of executors. So this is how we share a serverless pool. But we change the association as the job is running, and this is how we are scaling the different applications up and down, right? So you see here, the orange application has 2 executors. At some point, the orange application is going to be scaled down, and one executor is going to be taken away from the orange application and assigned to the second application. The blue application, in this case, has finished. So, right. So this is just showing a more detailed picture on how the scheduler is built. This is obviously a key component in this system. I don't want to go into too much details here, but the scheduler is having 3 important subcomponents, if you want. It has a core scheduler that computes the schedule for tasks based on the application structure. The scheduler is basically computing the schedule based on the number of tasks in a stage, but also based on how long these tasks are going to run, right? Because you may have one stage with a few tasks, but those are heavy tasks that are going to occupy the nodes, the GPU or the CPU for a longer time. And then you have another stage with a lot of tasks that are actually short. So the scheduler is differentiating between these different tasks. And how is it doing that? How does it figure out whether a task is running long or short? The scheduler is using machine learning for this. It is trying to predict task run times based on previous runs. So this is what the Oracle is doing in this figure. And then we have a resource manager. The resource manager takes the schedule and decides which set of executors to associate with this particular stage at this point in time, and then instructs the driver to connect to these executors, so basically switch the connections. So if you want to know more about how the scheduler is implemented, there is a paper on this. We published at last year's Hot Cloud workshop, so that's just in case you're interested. So now we have put a video together that shows this whole thing in action. This is just to give you a little bit of navigation opportunity here. So the screen will have all 3 applications lined up on the left-hand side in these 3 terminals. We have one machine learning application here. This is grid search, and then we have 2 SQL queries. And this is kind of like the main use case that motivated this work, right? You have one long-running background job, typically machine learning training, right? And you have these short-running analytics queries that they come in. And the way you want the system to behave is that it is offering a fair share of the resources among these applications. So if the short-running queries come in, they will get some resources from the long-running query. The long-running query is going to be squeezed together a bit, right? So then on the right-hand side, we show in these 2 windows, we basically show how the resources, in this case, the executors, are shared among these different applications. So let me see if I can get the video started. Here we go. So this is, does it show? Okay, so you see, we start the machine learning app first. So this is started right now. You see at the bottom, this is the green application. It's running on all executors initially because the serverless pool is basically free, right? You can grab all the resources. The second application is started, so you see the SQL application is started, and it starts to take a few executors, so I can't read the number myself, but you can see the yellow application is starting to grab a few executors. These executors are taken away from the machine learning app and reassigned to the SQL app. And now the second SQL application is started, and the same pattern continues, so some of the executors are shuffled around between these different applications, right? So this is going on now, so all of the applications have, these 3 applications essentially sharing the resources of this serverless pool. And now we see both SQL applications have actually terminated, right? So the machine learning app training app is essentially the only remaining application on the serverless pool. It has all the resources back that it had initially. I think we can stop at this point. So the machine learning application is just going to finish, and the serverless pool will be empty again. So now, this is another interesting just picture illustrating the same thing here. You see on the y-axis the different executors, and on the x-axis you see time, and you see how the executors are assigned to the different applications. I think this is actually the matching figure to this recording. Now, so we have now pretty good understanding how the system works, right? Now, let's have a look at performance as well. So we evaluated the system on a 16-node cluster. So the cluster is divided up into two parts, two 8-node clusters. So one part we exclusively use for storage, and the other part we use for compute. And this is IBM, the nodes are actually IBM Power-Minsky nodes with half a terabyte of RAM, some flash. As I said, 100 gig network. In one of the experiments, we artificially throttled the network to be 10 gigabit. And then each of the node has a GPU as well, which we are using for the machine learning workload. And we evaluate basically three queries or workloads. One is a logistic regression workload, machine learning workload that is implemented using the Cocoa framework. And then we also evaluate two TPCDS queries that are slightly different. So let's start with the machine learning workload. So this is the figure that shows basically the time per epoch averaged over many, many iterations, right? And the basic question we're trying to answer in this figure is how much of a performance penalty we get due to the fact that we are basically storing or constantly caching, rereading the input data set from a remote data source, right? And also the fact that we have to store shuffle or broadcast operations. Actually, there's no shuffle in this experiment, but broadcast operations on an external data source, right? How much of a performance penalty we get for that? And so what we did is on the bar on the left-hand side is basically a reference. It's a reference performance. This is showing that particular machine learning workload on a dedicated cluster. So this is a non-serverless setup, right? And there's no gray bar in this setup because the data set is cached, and it's basically, the reading is basically amortized over many, many runs, right? Now, the next part to the right is showing the same experiment, but here we mimic the case where one of the tasks per stage is rescheduled on a new node. So in every stage, one of the tasks has to reread the data set, right? There's currently no way to really run Spark in this way. There's no way to dynamically change the executor. So what we did is we just randomly pick an executor per epoch and make sure that the task is rereading the data set from HDFS. And the HDFS cluster is on a separate set of nodes. Right? And you see that adds a bit of overhead, not like dramatic, but still quite a bit of overhead. And then in the next bar, so the third bar in this figure from the left side, we are actually running an experiment on our serverless deployment. Right? So here we're using Crail for the input data set as well as for the broadcast objects, and we are actually also using Crail as a communication store to communicate the new model to the workers, right? I mentioned before that Crail is a high-performance store that runs on RDMA, but it has different storage and network backends, and it can also run in the cloud on a regular TCP-based backend that is not particularly optimized. And the third bar here is showing this setup. So this is a setup that you could easily run in the cloud. And you can see we can bring down the performance, actually. So we are not only reducing the overhead, we are actually faster than the cluster setup, right? And then the last part in this figure is this is where we are throwing in all the network stack operations and optimization. So we are throwing in all the RDMA part for these things, and we can bring down the performance even further with this. So in the end, we are about a factor of 2 faster in our serverless setup than using vanilla Spark on a standard cluster. This is pretty nice. Now this is showing similar setup for a TPCS query. It's a slightly different setup though. So again, on the left side, we have a sort of a reference experiment where we run that particular query on a standalone cluster. But here we actually throttling the network to be 10 gigabits, so to sort of reflect a cloud-based setup. This could be very well what you get in the Amazon cloud if you're running this, right? This gives us some number. And then the next bar to the right is showing on the same cluster, using our serverless deployment, what the query gets. And you can see actually, so here we actually pushing all the state to a remote storage cluster. And you can see that increases the runtime, right? So we're actually paying some price for storing all that shuffle data on a remote, on a set of remote nodes, right? So this is really what happens here. So, but this is really showing that on a slow network, storing these intermediate data sets on a remote node is not going to work. Right? At least not for this type of queries. So what we started to explore is, can we upgrade the cluster from a 10 gig to a 100 gig cluster, improve the network, and then solve that problem. So this is what the third bar is about. It's the same experiment, but this time on a 100 gig cluster. So we get the performance down a little bit, but we're still slower than the 10 gig cluster experiment. And then in the last experiment, we throw in all the network stack optimizations, and we bring down the performance to a value that is lower than the original cluster. So the basic takeaway here is you need both fast hardware as well as software optimizations to make serverless computing work effectively for this type of workload. And this is the final experiment I want to show. This is also a TPCS query, but this is a very short query. The query runs just for a few seconds. But if you deploy that query on a Spark cluster, most of the time is actually spent for ramping up the executors. Right? So you see the blue part is actually ramping up Spark, and the red part is just the query execution. So most of the time is spent on actually bringing up the cluster. And obviously one big advantage of a serverless pool is that you don't have to bring up the cluster. So you can see the middle bar here, the blue part is reduced. Right? Unfortunately, we still have quite a bit of overhead, and we're working on reducing that further. What is interesting about serverless pools is that you basically, the typical way of using them is you start them once, and then you use them for a longer period, right, for multiple queries. And at some point, the serverless pool will start to get warm, in the sense that all the compute engine is getting chitted, and the cluster is just executing faster. And this is what is shown in the last bar. We run the same query again, but this time, not only the infrastructure overhead or the initial overhead is reduced, but also the query time is reduced because the cluster is chitted, the code is chitted, it's very efficient to run that query. Okay, this brings me to the last slide here. What I try to show is that efficiently operating serverless deployment is difficult. There are numerous challenges. In this presentation, I spent a lot of time talking about storage-related problems. The fact that you can't keep data local to the compute nodes because you want to scale up and down the compute nodes, so you have to push data out. Right? And I've shown how we can turn Spark into a serverless framework that supports arbitrary workloads like machine learning and SQL. We basically made two modifications to Spark, one at the scheduler to allow the drivers to share the executors, and the other modification was to actually change the way intermediate data is handled using Apache Grail. And yeah, because we're using Grail also, we can effectively leverage RDMA hardware, Flash, and so on for this. I want to mention, I mean, we are working on a few future work items. Obviously, we want to containerize this whole thing so that we can deploy it in the cloud. We want to add support to dynamic repartition, because if you scale in or scale out, Italy, you want to change the partitioning as well. We want to add support for automatic caching and more sophisticated scheduling policies and many more things. Here's a set of links. Again, there is a talk from last year about the running Spark on RDMA, NVMe, Flash type of environment. I didn't have time to go into too much details about that. There's the Crail website that describes how the storage system works. The entire code we use for this is open source. It's going to be open source. We are just still in the last final steps to make it. But the repositories are already created, and it should be open source in a few weeks. So you can literally run the same serverless setup on your own cluster. So if you're running an organization or a research lab where multiple parties are executing queries, you can have a shared serverless pool using this code base. And then I want to thank the team also. As I said, there's a large team involved in this. This has been a lot of work. So yeah. With that, I conclude, and I'm happy to take questions.